Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we search for the theories that are going to change the world. And a huge part of this program has been explorations of quantum physics and trying to reconcile the bizarre behavior of things that are happening at the fundamental scale with our everyday reality. And over on this program, we have come up against the realization that perhaps the reason that quantum mechanics seems to make no sense is because we have completely abandoned the notion that there should be physical mediators of fundamental phenomena like light, gravity, electromagnetism in general, magnets. All of these invisible actions require some physical process in order to explain them to a rational mind. Problem is, quantum mechanics is just equations that describe how things unfold in a probabilistic sense. It doesn't provide us those kinds of physical explanations. There used to be a way of penciling in these physical mediators for most of the history of mechanical inquiry, going all the way back to the Greeks, which is this stand-in concept of the ether. The ether was abandoned at some point around the turn of the 20th century for various reasons, which we've elaborated on other programs. We're going to get into it today. But one popular approach has been to model that mediator substance as an elastic solid of some sort, where deformations in that medium account for the fundamental phenomena, all the way from electrons to light itself can be modeled as perturbations of this squishy material that occupies the region in between, planets and people, things like this. So with us today, we have Chantal Roth, who is a computer programmer that simulates how these basic phenomena can be understood using an elastic ether conception.
And this conversation with her is the first of two parts, where we really start out by laying out the elastic ether theory, how it works, why it's important, how it is different from the luminiferous ether that preceded the turn of the 20th century. And then in the next conversation, we get down to brass tacks, where we figure out how elastic ether models things like light, electricity, gravity, magnetism, mass, all of the big questions that fundamental physics has equations for, but does not have explanations for.
One other thing, we have this new segment going. We are in episode 8 coming on for Paradigm Drift. Paradigm Drift is a show that happens once a month. You, the audience, get a chance to put your name in a hat, and you have a chance of being selected to tell your story of how something works in the universe. So sign up. You can learn more about that program down below at DemystifySci.com.
And so before we get to the conversation, I have to say a couple of things. The first is that we are a program that is supported exclusively by our listeners. We do not want to sell you weird tchotchkes. We do not want to have some kind of steady stream of weird sponsorships for slightly awkward and trashy products. We really believe the fact that we produce conversations like nobody else on the internet, and in order for us to be able to continue to do that, we need your help. You can come to patreon.com/demystifysci and sign up to support the podcast for just 75 cents a week. If you can do that, that means that you are going to ensure that we can keep growing this from being something that we just produce over Zoom in our living room to something that is a much more polished, much more refined, much more beautiful exploration of ideas that really showcases what it means to wrestle with understanding something that is obscure and difficult. But we can't do that without you. So come over to patreon.com/demystifysci today and sign up. There's also two other ways in which you can support the podcast. Number one is Shiloh and I have designed some sweaters. They're down in the shelf below. There's also a link, I think, in the description to our Fourth Wall shop. And at the Fourth Wall shop, there is one last thing that you can look at, which is our vinyl record. We have a band, it's called Secretary of Nature, and we have printed vinyl of our first record called Everything Is So Good Here. It's kind of rock and roll, it's kind of weird synthy stuff, it's atmospheric, it's two sides of just explorations of what it means to be alive and how everything is both so good and so bad and so everything all at once. And people keep telling us that they have no idea what this music sounds like, and we've gotten kind of tired of our theme song. And so from here on out, we're going to be playing a couple seconds of it instead of our theme song as an introduction to our conversations. So enjoy this little selection that leads into the conversation with Dr. Chantal Roth about the nature of the elastic ether.
I have seen a man never come alive, just another drone in the hive.
Yeah, why do we want an ether? So that goes back to the motivation. So I always wanted to know how things work in nature, like magnets. Specifically, for instance, what's between the magnets, right? How does it work? And all the modern explanations is just mathematics, but they don't really explain anything. The thing about how virtual photons are exchanged doesn't really explain much, because how do you get attraction with the exchange of photons? Just never really made sense to me. And I never gave up to dig further into these topics. And that's just one of many. Like, what is spin 1/2? People say it has angular momentum, but yet the electron is supposed to be a point particle and it's not spinning really. So how does that work, right? And then the speed of light, like, why is it supposed to be constant, right? It's just presented as a law, but without really an explanation. And then even worse, the quantum physics, you have like, I don't know, 8 or 9 different interpretations, but none of them really explain anything either. I mean, you have the many worlds, which sounds cool, but what's the mechanism? And, it doesn't really explain any of these questions either. And, the thing is, it's really strange, I think, to have so many interpretations of something, because when you think about a car, like, we know how a car works, right? We know exactly all how the pieces go together. There's no question. We don't have interpretations. And I think that understanding helps us to develop new cars, for instance, right? Same with computers. But in quantum mechanics, supposedly, this is all kind of magical and we need all these interpretations. That's kind of a red flag to me, So it seems like maybe we don't understand everything, right? And of course, when I kind of started, I was looking at these interpretations. And the one that's probably the closest to what I'm going to talk about is the pilot wave theory, because there is actually a wave, but then on top of that, I still have these particles. So that's still weird. So now you have two things. Now you have the wave and a particle. So I figured, well, maybe there must be something else, right? And of course,
can I just elbow in for just a second, just to catch people up? Just the bare bones, dumbest level explanation of this is that there is something that causes action at a distance, whether it's gravity or magnetism, and we generally learn the mathematical equations for that, right, in high school and college. But the idea that there should be something that's actually mediating this, some physical structure that does it, has just been pushed to the sideline. And you mentioned that it's very difficult to make sense of how, two virtual photons pull on each other or whatever it is. I'm not sure if that's the right way. I'm not an expert in virtual photons, but that's really interesting that you had that sense that it didn't make sense. And I wonder if you encountered colleagues along the way who thought it did make sense, and why you think that most people who are experts in these fields do think it makes sense. Like, how does that make sense to them? How do they justify these magical things?
I have so many conversations about this, and it's like I don't know if it's kind of brainwashing or something. They just learn this in school, right? Oh, it's been proven there's no ether, and that's it, right? End of story. And it's just, they don't even want to think about this, it seems to me, which is very strange, because there's really no mechanism of any of these. Like, general relativity, what's the mechanism? How does matter curve space? All these things, there's no explanation. And so, of course, the challenge of finding a solution is there's many puzzle pieces that have to fit together. Like, you can't just look at general relativity. It has to also work with special relativity and the Maxwell equations, and with, Schrödinger, and it has to work with a wave particle duality. So, and there's some people who find niche solutions here or there, but you need the whole picture. So I've been trying to put together this overall picture. Hopefully that makes sense for all these different areas, right? I thought maybe we could start with Einstein, actually. and general relativity. And then maybe from there go to special relativity and all these other topics, if that sounds okay.
Well, I think we should go back a little bit further, because it seems to me that for most of human history, or most of the history of rational inquiry about natural mechanics, which, depending on which culture and skipping over dark ages and stuff, almost everybody believed that there was some sort of mediator for actions.
Oh, absolutely. In fact, even Lord Kelvin, for instance, he thought that the universe was an elastic solid. Also, Maxwell, he had this mechanical model, and he viewed, for instance, the electric field as displacement and magnetic field as a kind of rotation. And also Stokes, from the Navier-Stokes equations, he thought that the universe was actually an elastic solid, and he thought that light waves were transverse waves in this elastic solid. And the problem that he had, though, he didn't know how Earth could move through it. So at that point, they had no idea, right, that that matter also has wave properties. So he was puzzled by that, and he kind of ended it there. Also, actually, Newton, and I will talk more about him later, but he actually had the idea that the universe might be an elastic solid, which is pretty amazing. That was like 1704, right? And there are many other scientists. There's Lorentz and Descartes and Helmholtz, Fitzgerald, Heaviside. Many people have had the same idea. So, and also there's some contemporary scientists as well. So it seems to me it's not such a crazy idea to think about this. I think it's really worthwhile to explore. And so,
what went wrong then? That's the weird thing, right?
I'll definitely get to that. So the thing is, what Einstein said, and I mentioned Einstein because many people agree with Einstein, right? Most people in modern physics, they would agree with him. So this is usually a topic that people can still agree with, right? You have some common ground. And he said that according to general relativity, space is endowed with physical qualities, right? So in this sense, therefore, there exists an ether. That's what he said. And he also said that according to general relativity, space without ether is unthinkable. So he went as far as saying we do need an ether. So the question is, why did people abandon this, right?
Well, he said something really weird because he treated spacetime as, in his 1920 address to Leiden, he talks about the ether and he calls it a non-kinematic ether. And I've always wondered what he meant by that, because it's obvious that he's making he's making some concession to the fact that there must be an ether, and yet I almost feel like what he's trying to say is that it is not an ether that is detectable as something external to our own system. Like it's not you can't apply some kind of kinematic equation to it because it's outside of you. It's almost
could make sense. Because it's not like a separate, so let me think about this. What does it mean space is endowed with physical qualities, right? What could that mean possibly? I mean, what do we know about these properties of space? So we know it can have curvature, right, from general relativity. So space is something that can curve. We know it can ripple.
Well, that's what's weird, right? Because do we know that space can curve, or do we know that objects have curved trajectories? Like that's
true,
right?
But why would they, right? So we can view it either way. We also know that it can ripple, right, based on LIGO experiments where the gravitational waves are sort of transverse waves. It must be able to support transverse waves, so we know that. So if you think about what kind of properties would space need to have, well, it can't be a gas, right? Obviously, because a gas couldn't support transverse waves. It can't be a liquid either for the same reason. So the only thing that's really left, it's got to be really rigid, right? In order to support.
It's got to bear tension, waves. Right?
Yeah. It basically needs to have properties of an elastic solid. If you consider the ether as an absolute medium, and if the speed of light is constant in that medium, let's say like sound in air or in water, then of course, if the apparatus is moving, the light beam is making, instead of going up and down, it's a triangle, right? So it takes longer now for the light wave to go up and down. Then if it was at rest, then you could just go up and down. It's like the Pythagorean theorem.
Mhm.
And this is the one direction. And in the other direction, if the apparatus is moving to the right, as it's moving forward, right, the path is shortened. And so it will be faster than if you were at rest. On the one way, and then the back way, it would be, so one way will take longer and the other way would be faster, basically.
I see.
And so when you do the calculations, you would, it's a very simple calculation, really. You could see a difference, right?
Mhm.
And this difference you can detect through the interference pattern. But that only works if the apparatus is solid and doesn't change the direction, doesn't change in length, right?
Mm-hmm.
So you've already mentioned the word ether a little bit, and it's always a bit difficult because people have different imaginations what that might be. And when I first heard the term, I thought that was kind of crazy, crazy idea. So it's not like we can't think of it like a gas or something. It's more space itself has properties. So the vacuum of space is like an elastic solid. It's not obviously made of a material we know. So it's not made of atoms, right? It's not made of any matter that we know. It would have to be something else that we don't know. We just have to have a name for it. Like sometimes people call it fabric of space-time, which is kind of similar. Except when people talk about this, they often mean just mathematical, right? Now,
Is this different from the idea that there's some kind of 0-point energy or quantum foam or any of this? Because if you look at I was looking at as one does, I was looking at the equations for the quantization of photons.
Mhm.
And the quantization of photons in the electromagnetic field is given by, it's like h bar times the frequency of light, and it's multiplied by n, the number of photons, plus 1/2. And so even if you have no photons present, you still have some background energy that's remaining because you have this n plus 1/2. So if n is 0, you still have a little bit of energy left. And so is this kind of what you're pointing to, this like fabric of space-time that's detectable through the fact that there's this background vibration of the universe?
Yeah, in that model, basically, the whole universe is like one gigantic, you could picture it as a translucent elastic solid. And sometimes I joke about this like a Jello pudding, right? Just a gigantic thing that can wobble. And the whole thing would probably be vibrating, even it's not, everywhere a little bit. So I could imagine that this might actually be, the 0-point energy. And
I feel like we've used that word elastic maybe 4 or 5 times now. It might be worth explaining to people what elastic means exactly.
So elastic means it's not, if you have like a really hard crystal and you hit it, it will break. Now elastic means it's like a rubber. Rubber is elastic, so it doesn't break. You can bend it, you can push it, you can squeeze it, and it wants to go back to its natural state. Imagine, a cube of really hard rubber. That's elastic, right? So you can wobble it, and you can, have indentations, and it transmits waves. And in the case of the elastic solid we're talking about, the speed of a wave in a solid depends on the stiffness of the material normally, and divided by the density. So you could imagine, and the speed of light is really large. So if you look at the numbers, it would have to be extremely stiff. I mean, a lot stiffer than diamond, for instance, like 10 to some crazy number, like 10 to 30 times stiffer than diamond. And the density would have to be low, actually, to be able to support such a large speed of light, right? So, yeah, I mean, if you want to picture, I like to have mental pictures, and I like to visualize it as some kind of like glassy type of structure, right? So actually, this brings me to Newton, because Newton, he thought of this already in 1704. I just found out like a few months back. I didn't even know. Did you know this? I mean,
no.
This is pretty amazing. And if it's okay, I'll read a small portion of what he actually wrote in 1704. He said, "Does not it's kind of old English, so I hope I can pronounce it. He said, does not the refraction of light proceed from the different density of this ethereal medium in different places, the light receding always from the rarer part of the medium, and is not density thereof less in free and open spaces void of air and other grosser bodies? And he also said, is not this medium much denser within the dense bodies of the sun, the stars, the planet, and comets than in the empty celestial spaces between them? And he also said, and though this decrease of density may at great distances be exceeding slow, yet is the elastic force of this medium be exceeding great. It may suffice to impel bodies from the rarer parts of the medium towards the denser with all that power which we call gravity. And I think, oh my God, when I first saw this, I'm like, this is exactly what I've been thinking about the whole time. So, and I really, if it's okay, I want to dig into this because that really explains how general relativity can work in this model. So what he was thinking is that space literally is like a glass in a way, but it has different refractive index. So if you wear glasses, you know how light can bend when it goes from air to through glass, right? And that's because glass has a different refractive index than air. And that's because in a medium with like glass with a larger refractive index, the light slows down. And this causes the bending of the light rays. So he was literally thinking that where stars are and planets, there was a denser, optically denser space than far out. And in that case, gravity is nothing but refraction, which is like so amazingly simple, right? And I'm going to make an example to you that something you can do in the kitchen.
That makes sense to you? That didn't make sense to me. Did it make sense to you?
I mean, it's the idea that in places where there is greater density, there's some bending of the paths that objects follow that is the result of said density. Where it's like, if light goes through air and it hits a lens, the structure of the lens is such that it changes the path that the light travels. And it sounds like what Newton's saying in these excerpts is that there's something about the elastic material and its density that causes that refraction of matter as it moves through these different densities is what causes gravitation and gravitational motion. Which is crazy because where he wrote this in the second
4, can you imagine? And he was forgot them. Like, why didn't people pick it up?
Well, he makes this thing where he's like hypothesis non fingo about the cause of gravity.
I'm not sure that's a cause.
Yeah, I guess
though,
probably I don't know for sure, but I can imagine at that time again, light is easy because they would think the light is a wave, but matter seemed like it's particles. How could that move through a glassy type of ether, right? That's really a big problem. So. But back to the refraction, there's something an experiment you can do in your kitchen even. So you can take a little aquarium or something, or a bowl of glass, and you fill it with water, and then you put a lot of sugar in it, like several kilograms, and you have to make it so that at the bottom there's most sugar, and then you have to make sure you don't stir too much. So the idea is to get a gradient of sugar. So at the bottom there's a lot of sugar, and towards the top there's basically only water. Now, when you take a laser, you shine it horizontally into the bowl, it will bend down.
Whoa.
And that's so cool. You also on YouTube, you see some videos. That's because there's a gradient of refractive index. So because the more sugar you have.
But do you see how I understand that we can parameterize it in terms of there being a gradient of refractive index, but it doesn't tell us why it happens that way. Like we still don't have like a mechanistic cause for why the light is appearing to bend the way that it does, right?
You're like, why does the gradient of refractive index?
Yeah, it's the speed of light is slowed down.
But why?
In a material. So the optical density, I don't know the exact details, but this is something that's well known, and it's also used in there's an optical mechanical analogy of general relativity where they use Einstein's equations in optics. Though they apply the same equations in optics, so the simple explanation is that the higher the refractive index, the slower the speed of the wave is.
The
And so
wave,
when you have a
the waves
wavefront,
get truncated, so the wavefront appears to slow down. But
it
have you
appears
seen
to
like
slow
a
down. It appears to bend just because of because when you have like a wavefront like this, and it starts to hit a material, it will start to slow down here, and so that's why you get this.
I mean, I think the reason that it slows down is because the charged particles in the material actually set up their own oscillations that in some sense phase cancel the primary electromagnetic stimulation. And so you get truncated waves because of this phase offset, which results in the appearance of these waves slowing down. But the interesting piece is that you still have an active system that's in some sense emitting electromagnetically in a way that interferes with the incoming stimulation. Right. So it's a very complex active antenna structure that's actually causing this, right?
Yeah, in a real material, like in a glass, for instance, but like when we talk about the speed of a wave, like the speed of light, for instance, in the elastic solid universe, in general, the speed of light depends on the square root of the shear modulus divided by the density. So if there's some reason that the shear modulus gets increased, or if it gets decreased, the speed of light would slow down. Or if the density increases for some reason, the speed of the light wave would slow down. And that's true for any material. So any solid material, the speed of the wave in that material depends on the shear modulus, and it depends on the density.
Yeah, like Charlotte and I were talking about this the other day. It's because the shear is a measure of how difficult it is to displace something. Like how resistant is it to being moved?
It's like stiffness, right? Yeah, exactly.
I guess that is true for phonons, for sound waves in materials, or however you want to call it, displacement of subunits in materials and so forth. But when it comes to light, the reason that we perceive a difference in the speed of the wavefront inside of a refractive medium is not because the light, it's not because anything to do with the density of the medium or anything like that, or the stiffness. It actually is just because of these out-of-phase standing waves set up by the new electromagnetic oscillators in the lattice of that material that are phase canceling the incoming signal. Right?
Yeah, that's true. Because in a real material, of course, the light is actually a wave of the ether, and so it's now in another material. So that's why it's an analogy. But it's true for, like, if you take a sound wave in metal as an example, you use that same formula, and you could do the same thing. You could change the stiffness, maybe by heating it or something, right? Or by changing the density, you would get the same effect. So that's true for like sound waves in ice, or basically any mechanical wave, like for phonons also, right? In mechanical waves, the speed of that wave is determined by the shear modulus.
I totally get that, and I'm 100% agree. And if there is an ether, or if the medium must be extremely rarefied and extremely stiff, like that makes perfect sense to me. The analogy with refraction that Newton brings up and that we're discussing, that falls apart a little bit for me, because the mechanism of refraction doesn't seem to have anything to do with stiffness or density. That's all. It's
just the speed of light that's different, right? Because as soon as when you have a wavefront, and if the speed of the wave changes, unless the wavefront is exactly in line of how the gradient changes, then it would just slow down and you wouldn't see any bending. But when the wavefront comes at an angle and it starts to slow down, then some parts of the wave are already in the slower parts, and some parts are still in a faster part still, right? They will catch up, and it looks like it's bending just because of there's a gradient of the wave speed, and it's very easy to see in a simulation. It's a little hard to explain without simulation, but this is well known, and it's very easy to simulate, right? You need just a wavefront, and you start slowing down this part here, right? This part will slow down, whereas the other parts are still approaching. This will look like a bending. And there's nothing, strange about it. This is well known. And in fact, if you just Google it, optical analogy of general relativity, there are many different papers about this also. Like, for instance, there's even something called optical black holes. If you've heard about this, basically, you can imitate a black hole in optics by using such a smoothly increasing refractive index. So imagine you have like a kind of like a metamaterial like glass, and as you go inward, you increase the refractive index further and further and further. You would then see light bending and so much that it will no longer escape. And there have been several papers on this also. So people are actually using this optical analogy of general relativity.
What's the density that you have to increase the medium to in order to get that kind of optical effect? Do you know? Is it
I don't know the numbers. What I do, I
Is
run a
it
lot
density
of
based?
simulation.
They're doing this by density. Are there actual demonstrations where you change the density of the glass or something? Hey guys, remember, we can't do this program without your support. We are not sponsored by anybody. We're not selling you anything we didn't make, but we need you to come over and check out how you can get involved in supporting the program at patreon.com/DemystifySci.
there's some kind of experimental process by which you can create a system that has this change of refractive index. And as you change the refractive index, it creates this sort of pattern. But I think that it's really important for us to get the sort of the big ideas on the table and then take apart the details. What do you think?
Yeah, absolutely. I still think Newton has no cause, though. It's just,
Perhaps,
yeah.
but it's like the final cause. So we were
I
Chantal.
think he has a good analogy. I think
Yeah.
he has a good analogy.
Yeah.
I think these are all good analogies, but I don't think that they're mechanically identical. They're analogous processes.
Yeah.
Yeah.
And so Chantal,
So are you saying that the speed of light does not depend? So which part is it that you're not sure about? Is it the part where you say the speed of a wave is not a function of stiffness and density, or is that what you think? Or which part do you think?
I think that the analogy to refractive index is an analogy. It's not a mechanical identity. Like I think that it is absolutely true that the wave speed depends on the things that we specified for waves and materials, and that we should expect that from our elastic medium that's transmitting these things.
Yeah,
I just think that
refraction. I can send you simulation. It's very, if you just Google it, this is very well understood. So all you need is as soon as the speed of the wave changes in some way, you get refraction. You can do this with any wave in any medium.
Yeah, I'm a little bit I'm not totally following your objection.
well, the cause of the wave changing in the medium, in the refractive medium, is not just a density or stiffness based cause. Refraction is not based on stiffness and density.
Specifically refraction of light.
Yeah.
And the reason that you're saying that is because you're like, there is a feature of longitudinal waves, which is when we talk about phonons in materials, when we talk about sound waves in materials, we're talking about the square root of the stiffness over the density gives you the velocity.
Yeah.
But what I think that Shiloh is saying is he's like, light is different because there is some active process by which it is being transmitted through the substrate, which...
Oh, I see what you mean. Well, of course, see, the analogy that doesn't work, the part that doesn't work is because we are talking about light, which is a wave in the ether, and I made the example of light in a material, of course. So light is not a wave. This is, of course, a little bit different. I agree with that. Yeah. So what the correct analogy would be a sound wave in a metal. You know what I mean? That would be, if you want to do the correct thing but of course you can't really visualize that well. So if you would basically take a sound wave in metal and you change the density, then you also get refraction. But it's kind of hard to visualize because it's easier to have glass and light to picture it and simulate. But it's, yeah, you're right.
Well, I think that this actually goes back to something that Faraday discovered. So in terms of the ether, I think that there's something really interesting historically, which is that sometimes it takes us a really long time to figure out how pieces of science fit together, especially when they are particularly hard to see. And so in the 1840s, Faraday does an experiment where he demonstrates that you can change the polarization of light as it travels through certain substrates. And the place where he finds it is but you can change the polarization of light with a magnet as it travels through certain substrates. This was the first time that anybody was able to show that light and magnets had any kind of relationship to each other. And I think that it's deeply significant that he showed that this was possible with inside of glass. Because
Yeah.
there's something about the atoms in the glass that are responding to the magnetic field that's changing the polarization in a way that's very, very different than what's happening to the light as it travels through air. And I think that that's what Shiloh is pointing to, which is the fact that there's something in the glass where the atoms are actively doing something to that light that causes it to behave the way that it does inside the medium. Whether that's the fact that you can, it's crazy that you can change the polarization of light with a magnet inside of a piece of glass, but not inside of air. Like, why is that?
Right.
I guess in general, I find myself tending towards analogies a lot often as well, because I think in some sense it's the quickest way to get people on the same page about stuff, but they also always break down that's in their details.
Yeah, we have to be careful. So the correct analogy would be a light in the ether follows exactly that formula, right? Of course, a light in the glass is made of atoms, which is much more complicated because light is bouncing around and all that. But still, ultimately, I think the analogy works still because it's true for waves in any material. So if you have a sound wave in metal, it's the same thing. So it does work. It's just the analogy has a little bug right there that you pointed out.
But I think that we've arrived at the same place where Shiloh and I have arrived many times before, which is the idea that if you have a wave, it's a wave of something. And there are very, very clear equations that tell you how to relate the speed of the wave to the stiffness and the density of the substance.
Can I just plug one paper too? There's a paper by Kirk McDonald from Princeton where he does 5 or 6 different analyses to calculate the stiffness of this. He's like, if there was a medium, he doesn't say that he believes.
He's calculating the thickness of stiffness of spacetime.
Yeah, so he uses a number of different methods, and he comes up with, like you said, these preposterous, 10 to the. Right? It's something. There's a whole range. I think it's from 10 to the 20th all the way up to 10 to the
130 or something. It's insane.
It's unbelievable. But there's we can unpack what that actually means in physical terms in a second, because it might not be as crazy as it sounds. When you start thinking about the low density factor, but we can get back to that.
So one question, of course, if that's the case, let's pretend for a moment, right, that there is an ether, and by ether I mean space has the properties of an elastic solid, kind of like a transparent medium. What does it mean in terms of the metric tensor? What does that mean? How does general relativity work, right? And so the way to picture the metric tensor, I think, is if you imagine we are now doing a simulation, we are putting in a little toy universe on our table, a little block of an elastic solid, right? And we kind of watch what happens in here. And that's important because we have to consider the kind of clocks we're using and measuring sticks. So we are outside the universe. We have our absolute clocks, because otherwise it's confusing, right? Because clocks always change. So we are outside. We are watching what happens in this elastic solid. And imagine we are now placing grid lines, like we've drawn, you see in my background, we're drawing lines on top, like a grid. So you have a 10 by 10 by 10 or something like that, right? Or coordinate system. And now imagine we place exactly the same cube right next to it to the right. But now we do some things to it. We squeeze it on one end and we pull it on the other. And then we also curve it just slightly. And now the question is, well, how do we now draw those lines, right, to match up again? Because now it's no longer right angles, and instead of 10 centimeters, it might be 11 because we pulled it, and the y-axis might be 9 centimeters instead of 10 because we squeezed it. So then, if I told you to please draw those lines, you would need some instructions how to do this. And so what I could do, for instance, I could create some sticky notes. And at each place in the left cube where everything's just nice and the 90 degrees angles, I place a little sticky note there that tells you how much at that point we are changing from this coordinate system to the other. So you would need to know, well, instead of 10 centimeters, we're going 11. So that's one number in the x direction. Then you would need to know what the y direction, instead of 10 centimeters, we go 9 centimeters, and also the z direction. But that's not enough yet because the angles might also change. It's no longer 90 degrees, right? So you need more numbers. You need some additional numbers to tell you, well, how much when you go to the right, is it a 90 degrees angle or is it 92 degrees angle? And so you need those additional numbers. And when I put those sticky notes into each coordinate, basically, you can now go ahead and you can figure out how to draw those lines in the cube on the right. And that's essentially the metric tensor. But of course, there's something missing. Do you know what was missing? Because I was just
the
talking
amounts
about
of
three
effort, I don't
coordinates.
know, the amount of effort necessary for those deformations or something like that?
Well, what was missing is I have only talked about 3 coordinates, not 4. The metric channel is actually 4-dimensional. There's time as well. So what does that mean in terms of time? Now, the thing is now we have to ask the question, what does that 4th coordinate mean? And so we have to think about what is actually a clock. Now, a clock is made of materials, and in the simplest way, you can look at it as the speed of light, right? Because imagine you have a laser and a mirror, and then one click of the clock is just, it goes up and down, and that's what we call like 1 ether second or something like that, right? We have our outside clocks where we can see how long it takes. And now when we have an elastic solid and we change the density, the optical density or stiffness in such a way that in one place it has a higher refractive index, then at that place light will be slower. And that means because light is slower, the clock will take more slowly as we see it from the outside. So imagine we have our meta clocks, right? We have our own normal clocks. They are not affected by anything we are talking about here. And we watch what happens in this elastic solid. So when we place this light clock, in a region where the refractive index is say 1, and we measure it, it's one tick is maybe 1 second. And then we place the clock inside an optically denser part where the speed of light is slower. If the path is the same, then the clock will slow down. So that's where
Isn't
time
the speed
comes
of
in.
light supposed to stay constant, though? For
Well, that's
all
a good
observers?
question. So this is a very important distinction. As we watch from the outside, so like we do it, let's say the experiment we did with the a metal, and we put a sound wave to the metal. We change the stiffness. The speed of that wave will change based on the stiffness, right? So like we do the same experiment now. We put this elastic solid on the table, and we change the stiffness in some way, right? So that the speed of the wave is actually slowed so the way we see it from the outside, we can see the speed of light slow down. The other question is, well, what happens to creatures in that elastic solid? And that's the important question, right? Imagine in this toy universe, we have these creatures, they have their little light clocks, right? What would they see? Well, and for them, yeah, even though the speed of light for us is slower, because their clocks are ticking more slowly, they would never know. For them, it would always appear as the speed of light would always be the same. They would not know.
And does this align with the way that Einstein formulated general relativity, or have we departed?
Yeah, matches exactly.
Okay.
Matches exactly, absolutely. That's the cool thing about it. The only difference is that when I talk about time, I mean an actual mechanical clock. The clock is literally ticking more slowly, and it's not like some abstract space-time thing. It's really, we have 3-dimensional space, and we have pi as measured in terms of actually speed of light. So the speed of the clock is really determined by the speed of the wave. So that's the speed of light. And if the speed of light slows down, the clock slow down, because if our clock is simply a light beam going up and down, when the speed of light slows down, the clock will tick more slowly also.
Okay, so this reveals perhaps a deep chasm of ignorance for me, because I thought that a big precept of Einstein was that speed of light is constant for all observers everywhere, no matter the frame of reference. And
that's
so there's
true.
Okay,
exactly.
So the thing that you're innovating.
So the way to see this is that because we are doing this experiment, we are like gods outside the universe. So when we look at this, or let's say you do a computer simulation, you program this, then you have the absolute outside view, right, of that simulation. And when you program this, you would have to make the speed of the wave to slow down.
And so you're like, okay, so the Einsteinian formulation of this puts us inside this block of Jell-O.
Yep.
And so anything that we talk about is happening inside the block of Jell-O.
Yes.
But you're saying that if we were capable of taking a step outside and standing next to the block of Jell-O and watch what's happening inside of it to like the little frogs and bugs, then we would be able to see something different. And so what does this model reveal? I think that you're trying to make some kind of connection between time and the speed of light and the material properties of the substance that have changed by the squeezing and the stretching. So like connect for me why this thought experiment is useful for understanding the way that the universe works.
So I'm trying to figure out a mechanical, simple explanation of how general relativity works so that really anyone can understand it. And the only thing really you need to know is the speed of a wave depends on the stiffness divided by density. That's the only, square root. But, basically, once that is clear, the speed of a wave depends on the stiffness and density. Then if anything changes, if the stiffness changes or the density changes, then the speed of the wave is also changed, right? That's just very simple material science. So if
do you have a sense, by the way, of why that is? Like, why do those two factors change the wave speed the way they do?
I don't know exactly. I see. Well, the thing is the way a wave propagates, right? You have the wave equation, and it depends. The wave equation depends when you have a displacement, for instance. So basically, let's say transverse wave, right? Imagine you have we put these grid lines onto the elastic solid, which might be easiest to see. You take one particular point, you start to displace it, right? Like imagine we have springs attached. It's probably easier to see with springs. Well, the speed of when you let go, right? When you let the spring go, it's going to affect the neighboring springs, right? And how long that takes depends on the kind of spring you have. And that's basically the material property, like the stiffness, right? If you have very loose elastic bands, then it's going to be really slow. But when it's very, very stiff, right? As soon as you start pulling on the one grid point, it will immediately also pull the next grid point right away, right? Because it's really stiff, right? And it's really loose, like shoelaces. So then it's not going to be very fast. So it's really quite simple.
What about density?
It's kind of related, right? So the denser it is, the slower it is. Because imagine if you had very very dense material, you have like 100 springs right next to each other, right? It takes a while to go from one grid to the next. This you have to do this 100 times. But if the medium is it's not dense at all. You have only one spring and then 1 meter the next. Well, then if the same stiffness, it will be much faster. It only has to go through one spring.
So it sounds like these properties, these fundamental equation we keep coming back to, stiffness and density, trying to understand the medium of light in this case. It seems like it's telling us something about an interconnected web of subunits that have specific connectivity that reflect why it is that they have these particular stiffnesses and densities.
The thing is, at least mathematically, it doesn't matter if it's continuous or not. So it's possible that it has like a smallest size. Like, of course, a lot of people think Planck length would be a logical smallest unit. But I don't think we can prove that yet, because even if it were continuous, there's an experiment we could do, and the thing is, so that
the basic equations come out of looking at the way that subunits interact, right? Like we modeled subunits attached by springs.
It's abstracted. The only time it matters is when the wavelength approaches the order of magnitude of the distance of the grid length. Then you see some effects where the speed of the wave changes. So the speed of the wave is constant, but as you approach the resolution, basically, of this grid, the speed of the wave gets a little slower. So in theory, if the universe had like a smallest size of, say, Planck length, we possibly could see, a delay in like really ultra gamma ray bursts. But I don't think we don't have the kind of capability yet to see those short wavelengths, maybe from really distant explosions or something. Then they would have to arrive just a little tiny bit later. So that would be an indication that there is a smallest size. Planck length.
I guess I'm not like so fixated on the smallest size thing so much as the way that we explain this relationship in materials in our everyday lives. Like the way that material science would address this is by the interconnectivity of subunits. That gives that reveals the particulars of the stiffness and the density of the material itself. And so I would expect that if we were talking about an ether in the same way, that we would also be curious about the arrangements and the for lack of a better word, the bonding arrangement
absolutely.
of the subunits that give it its particular properties.
And there are different authors. Like I have been working together with Marek Danielewski. He thinks the universe is essentially like a crystal, and he thinks there is like the smallest unit is Planck length. But then again, I'm not sure. I mean, it sounds plausible, but I don't think we can prove it yet. And there's another author, Robert Close. He writes about this too. He thinks it's continuous. So I don't think there's different opinions. So this is where people start disagreeing. But I don't think we have proof, right?
I would go with messy spiderweb personally, but that's just me.
That's another. Yeah, foam. Like you hear about quantum foam, or I don't know. It's also possible. Like that's speculation. I think even all these options would result in the same kind of observations that we can do right now. And so, one question, of course, is, well, if that's the case, right? How can matter now bend space, in quote? How can matter influence that? And there's basically an elastic optical analogy. So if we consider that matter is really also waves, standing waves, in the case of an electron, right, we have one aspect that's circulating, we have the spherical harmonics and all that, essentially really complicated wave, a soliton wave that's enclosed in some volume. It's really kind of the same thing. And so when we have mass, that means extra energy. So mass is then nothing else but, if you look at the particular volume, all the kinetic energy of the wave and the strain and the stress, the total energy there is essentially what that mass is. So that mass is basically the energy inside a volume. And in linear elasticity, when you have added strain and stress and all that can change the density. It's like added mass density. So, and again, as soon as we change either the stiffness or density, you would then have a change of the speed of the wave speed.
Wouldn't you expect that so in an elastic medium, you have a standing wave that has some amount of energy. And so you're saying that, okay, so the electron has this like spin 1/2, very strange harmonics. It's even for the simplest electron, it's complex. And then so I'm following you as you say that, okay, so matter does appear to be waves of some kind, because if you assume that, atoms are made out of some harmonic standing wave pattern
of something,
whether that's the elastic ether or whatever, then you're stuck with the fact that as you make it bigger and bigger, you have not departed from the frame that the mass is still, when you get a microphone that zooms you far enough in, still just the standing wave. Okay, great. But so then to say that the energy of that wave is the thing that gives it mass in the first place, that's the part where I'm not totally following, because mass appears to be I can't think of it except as a relational property. It's like about the ability to interact with something at a distance, right? So it's if you look inside of a gravitational equation, you have two masses at a distance will exert this amount of force on each other. Mass accelerating at this rate will give you this amount of force. And so it seems like mass is something to do with scaling how much force you exert on the world.
Oh, okay. Well, I think we have to go back to the refraction and the speed. The way we can explain general relativity is as we change the speed of light, and with that, the refractive index, right, of the elastic solid, which leads to refraction, then the larger the refractive index is, so how should I say this? The gradient of that refractive index is actually acceleration. That translates directly to acceleration. And you get the same, these pictures where you have a gravitational well, where you have like this, sometimes they show these rubber sheets and they put like a ball in it, and you see how you get the same kind of curving. And when you map it to the elastic solid with refraction, then the gradient, this is what we're plotting here, is actually the gradient of the refractive index. And that's corresponds to acceleration. So the gradient of this is the acceleration. So the force that we see, that the apparent force that, for instance, the Earth, quote, feels from the sun, is because there's gradient of refractive index. And because matter is a wave, a standing wave, if you do a simple simulation, for instance, in a gradient of a refractive index, the wave would be, looks like it's being pulled towards the higher refractive place. It's similar to the effect of a light beam bending, except, of course, when you have a matter, you have a standing wave, but it's the same effect. The wave will slowly refract towards, move towards the place of high refractive index. And that's actually Newton. He saw that too, which is pretty amazing. I mean, I don't know, he couldn't even do simulations back then, right, or anything. And he saw that already. That's when he wrote in the optics. He had that same thought, which is pretty amazing. And today it's much easier because we can do computer simulations, for instance, to see that, right? When you play, say, a circulating wave and you have a gradient of refractive index, you can see that how the wave will get sort of, it will migrate towards the place of high refractive index. And that's what I meant. That's basically what is the curvature, what we call the curvature of space-time. You could imagine as, well, how much does the gradient, what's the, how large is the refractive index? Or you can also express it as the speed of light. Like it's these are equivalent, right? So the larger the refractive index is, the slower the speed of light is. So you can express it either way. But the easiest is probably refractive index because the gradient of this is actually maps exactly to acceleration, which is interesting.
I want to make sure that I follow you up to this point. So I want to see if I can recount some of this and see if you tell me where I've got wrong. So do you imagine that you've modeled the universe as an elastic solid, but it seems like it's an elastic solid that has some parts that are dense and some parts that are not as dense. Is that true? So it's kind of a lumpy.
The meaning of dense can be interpreted as optical density, not necessarily actually more material, right? So it could be expressed in terms of stiffness also. It's easier to call it dense because it's nice to visualize, but I don't actually mean dense in terms of there's more ether or something. It's just, it could be just optical density, like Newton was saying, or stiffness.
This is where I'm getting lost. Okay, it's stiffer maybe.
Well, yeah, because stiffness. I mean, like, if stiffness and density are the two features, the two parameters that you can vary in order to be able to describe the material that has a certain speed limit in it. So, okay, so there's actually I just realized there's two things in here, right? Because do you think that the speed of light is actually constant? Because from the experiment that we did where we stood outside the block of jelly and we looked into it, it seemed like what you were saying is you're like, okay, so if you actually look at it, there's places where this fourth dimensional component of the metric tensor, time, as measured by the speed of light, is different because you've squished it or you've expanded it. And so it does seem like you're saying that the speed of light is not actually constant. And so is that true?
Outside observers, but of course, in reality, in our universe, there are no outside observers. So that's why I think most people will agree, anyone inside the universe, any creature, anywhere in this elastic solid, they would always measure the same speed of light. They would never be able to tell. But of course, when we simulate, let's say when we want to write a computer simulation, we need to have like a global clock to do the simulation, right? To update the screen like every cycle or so, right? When we do that, we have to actually change the speed of light to make it all work. Otherwise, it wouldn't work.
Why can't they tell? Like, why can't we tell?
Because all our clocks, even if it's a mechanical clock, right? There's something involved, like a vibration of some sort. And all our clocks are ultimately atoms made out of waves. So if the speed of the wave in the medium slows down, that slows down all the atoms, all the vibrations, it slows down light, it slows down any movement because we are all made out of waves, which sounds crazy now, of course, but I can also explain why I think that.
But no, it doesn't sound crazy at all, because if again, like we said before the break, if you break matter down to its simplest form, it is some kind of vibratory
and it's the same
wave.
Formula. It's the speed of a wave.
You guys are losing me there. It's just killing me. I'm sorry. Well, because a wave is an action.
That fine, but what I'm trying to say is that like the so if you assume that the universe is filled with some kind of substance, let's just say that there is we begin with a completely featureless universe that is just filled with substance, that is filled with whatever the ether is.
Like great, we can just draw like a grid with springs. It doesn't even matter. Like anything would work really.
But, but there's an assumption buried there, like that it's homogeneous.
Well, hold on one second. So we begin with a completely like with a flat sheet or volume
Jello.
Jello.
I like Jello.
Jello is great.
Yeah, Jello's cool.
Okay, so we begin with Jello, and then what happens? So I always try to imagine. Okay, so what does one atom look like? You have a vast universe and you have one atom. Well, what you have is you have some kind of, for me, I imagine that it's some kind of knot inside of the material that the Jello is made out of. It has motion inherent to it, which is its wave-like qualities, but it also has all of these particulate properties, which is, location and discreteness. And so
extension,
like volume. And so if you have a hydrogen, to me, that's some kind of wave-like knot in this Jello. And so the Jello analogy kind of breaks down because you have to be able to have subunits that are capable of pulling on each other. And then if you're pulling with forces as opposed to actually being interlocked somehow, then you have all of these questions of how is the force generating any kind of attraction? It seems like it has to be some sort of...
Like, doesn't the Jello have to be anisotropic to have atoms? Like, there has to be places that are different density, stiffness, that reflect more subunits doing more stuff at some places versus others, right?
Yeah, so the question is, why is there difference? And the difference is because when there are more, in places where there are more waves, so there's more vibration going on, right? That's basically all it is. If matter is just basically waves, so more matter means more waves, those waves change the property of the stiffness a little bit in that area, and that changes the speed of the waves.
So I think that the confusion comes down to this, which is that we're discussing the nature of light, where we're like, look, light is a wave, but the wave has to be a wave of something.
Yes.
In order for this to make any sense. And so we can talk about the ether, and so we can derive its stiffness and its density and come up with some kind of real tangible substance. And it's like, okay, so far so good. That's fantastic.
Yeah.
But then I think that the place where Shiloh is getting stuck is he's like, okay, so then what are we talking about when we say that matter is a wave? Like,
it's also a wave of that same medium. Okay, except the difference is light is a simple transverse wave. It's a traveling wave. It's a transverse wave that just travels. Now, when you have, say, an electron, you can imagine the wave going in circles instead. It's not the whole thing, right? The electron is pretty complicated, but one part of it, I think, is actually the wave going in circles. And Williamson, he had a presentation on this too. He was explaining why he thinks, you can actually have two laser beams and they create the positron and electron because it's the light waves, they were traveling waves as they approach each other, right? They start to then go in circles. And when you have the wave going around in circles, you have in a way, like some people call it, matter is just light that's trapped, which is kind of, I don't know, it's maybe the wording, it's very, the picture is nice, but it's not totally wrong, I think, because just, a standing wave, a soliton wave is one part of, at least for electrons, is a part of the wave is going in circles. For this, especially the spin 1/2 part, which I can explain a little later also, maybe. So
but it sounds like basically what you're saying. I think that when Chantal is saying that matter is a wave, what she's saying is that the same way that light is a wave, as a transverse wave of the ether, matter is a specific type of complex wave of the same substance.
Is there any material or Jello on Earth where you can set up these kinds of things? Like, can you take a Jello and have a standing localized wave?
Oh, that would be so cool. That's why I really, people should work on this more. I'm really hoping that some people get interested and actually do some more research in this, because that would be so cool if you could reproduce this kind of standing wave in like a Jello or some other material, right?
Especially if you could move the little standing wave around and
Isn't this what cymatics is?
It's not in a Jello though.
And it's not in a Jello, but okay, so this is the question. Can you induce cymatic patterns inside of a Jello-like solid?
I don't know.
Because
I
I
would
mean,
have
like
to
the
research it.
wave. So the crazy thing about the cymatics is that if you take a Chladni plate, which is this metal plate,
Mhm.
and you put it on top of a speaker, and then you sprinkle it with sand, and you drive the speaker at various frequencies, you
Yeah.
start to get these patterns.
Yeah.
Those patterns are two-dimensional representations of the three-dimensional mathematics for wave functions. They're basically they're
exactly.
planar
Harmonics,
harmonics.
yes. Mhm.
And the wave function of the electron is spherical harmonics. And so you basically
Yeah,
add another
exactly.
dimension and you go from, ooh, cool Chladni plate to, oh, that's really weird. That's the mathematics of the wave function.
Yeah, exactly. Yeah.
And so
And that's how by the way, that's where we get the shape of the atoms from, is
Oh,
modeling.
totally. Yeah, I wanted to talk about that too because it's just music, really, right? I mean, electron is just it's just harmonics, and I don't think it can be a coincidence that the shapes of the orbitals is just spherical harmonics, right? That seems like quite a coincidence. So, I mean,
I guess I'm just like this makes sense to me now. So that's really all that matters. I think I'm following you. The only piece that I'm unconvinced of yet, maybe you'll convince me of this, is that density isn't important, because and that the stiffness and density don't necessarily reflect the lumpiness of the situation, because one way to get stiffness and density augmentation would be to change the connectivity of the subunits. The other would be to increase the number of subunits.
Yeah.
And so I could equally model this. I guess the way Nastia had it was we're changing the knotting, like how these.
Yeah. I'm not sure if we can prove it either way. I mean, I think both models would work. I think both models come to the same conclusion. And, I'm not sure if it's even, I mean, that would be a good discussion to have with, say, Robert Close. He has studied that a lot more, if it actually makes a difference. But I think it's equivalent. And also there are different models. And this is the kind of disagreement, a lot of people agree, I think, that there is an elastic solid ether. But there's some details that people don't agree on. And maybe we'll just have to figure it out by either experimentation or, maybe there's some logical inconsistency at some point if you follow that path versus this path. But at least with the stiffness, it does seem to work. And so, I mean, maybe there's some place where it doesn't, and then maybe you have to also include density or even both. But with the stiffness, it seems to at least work out so far.
Yeah, maybe before we end, we can circle back on this question. I want to make sure that you get to present
there's a lot
all of the
more
ideas first, because I think I think it would be fun to circle back on it, though, because we can compare the sort of homogeneous isotropic version of this versus something that's more structured and ugly, and kind of compare some ideas there. But I don't want to derail this
Sure.
presentation for now.
Because another interesting part is with this very simple model. It's simple, right? When you have now a light wave that, say, goes toward a region with higher refractive index, the clock slows down, the wave slows down, but also the wavelength gets shorter, and that causes ultimately a blue shift. So someone sitting, like some creature sitting at the center of this high refractive index area, seeing a light beam coming in, would see a blue shift. And on the other hand, when a creature sends out a light beam from, a highly dense area to an area further away, the speed of light would increase, the wavelength would increase, they would see a redshift. And that's also what we observe in general relativity. So it's a very simple explanation.
But you don't think that the density is really different. You're making analogies, right?
So whether it's just as long as the only thing we need is that the fact that near massive bodies, either density or stiffness changes. And so that causes the speed of the light wave to slow down. And you can express this as refractive index, if you like. I mean, to me, it's easier to use the refractive index because that maps really nicely to acceleration, and it's.
I'm just confused because I feel like I'm sorry. I'm really sorry for just being a moron about this.
I think that Shiloh's confused because earlier you said that density was uniform, and that you introduced this term which was like optical density. And so you're like, the substance, the ether itself, is uniformly dense, but the optical density changes. And
yeah, that's one way to see this. And I've been using this messaging just because I didn't want to, there are different explanations for both. You can go down the route and say, well, maybe it's density that changes. But at least I've been focusing on the stiffness because the stiffness can explain why matter influences the speed of the light, because when you have more matter, you have more energy. And more energy causes a change in the in the refractive index in the stiffness. And so, but I don't know which one it is. It will work mathematically either way, either if you change the stiffness or change the density. I'm not sure if we can actually prove either way. I think both paths are, and some people will say, well, it's density. I'm not sure which one Robert Close actually uses. I would have to, the link I sent you, maybe we can take a look and,
But so I guess I'm just trying to make sure we will take a look. It is if I open up a browser right now, I will probably spend the next 15 minutes trying to get back to where we're supposed to be. So I'm not going to do that right now. But I guess I think that what you're saying is you're using optical density as a stand-in for the behavior of light.
Yes.
Not as a physical characteristic of the underlying ether. You're like, the light moves in such a way that optical density looks like it's different because of this. Got it.
Yeah, it's slowing down.
Does that make sense?
There's different ways how to express it and to make it sort of understandable, hopefully.
So you're using optical density because refraction is at the center of this for you.
Yeah.
So you basically have this like elastic refractive model, and the reason that optical density appears over and over again without us change, and we can deal with whether or not, because it seems like refraction does have something to do with like actual density, because with the sugar example that you gave us earlier, where you can take a light and you can shine it.
Because sugar changes the refractive index.
Chantal. It's so funny.
It's just there's an analogy about optical refraction to material refraction, which is definitely an analogy. It's not a one-to-one correspondence. Mechanistically, they're different.
Yeah, this is really funny because Shiloh and I have spent the last 2 or 3 days talking about how difficult analogies are and how they're both incredibly useful for science, but how often they create these weird little spurs on the sides of theories and explanations where you're like, well, hold on a second. The electricity is like water, but it's not like water either. I think that this is what we're stuck on, where we're really trying. Like we literally, Shiloh and I have the last 2 or 3 days, almost every single day, been having a discussion about the nature of stiffness and density and its relationship to the ether. Yes, absolutely. Yes, I swear to God.
Okay, sorry about that. I didn't know. Well, okay, let's just say the speed of the light slows down in areas where there's more matter, and matter is just waves. So maybe we can forget about the details for a moment, otherwise we'll be stuck here for a long time.
Hold on, well, so the speed of light slows down where there's more stuff?
Yes, more matter means more, and higher. I like to use a high refractive index because it maps directly. It slows down light, so high refractive index means slower light. From the outside, viewed from the outside of the universe. So only we can see that, of course, because we are doing experiments with these mini universes. Just to be clear. So again,
I see. Okay. I think I get it. So you're basically saying that like inside the universe, the entire matrix is compressed or rarefied in such a way that we cannot actually evaluate anything about the speed of light. But if we were to take ourselves out and to think about the underlying relationships in physics, what you're saying is that you would expect that near massive objects that light would be moving slower.
Yes.
Okay.
Exactly.
And the reason that light would be moving slower is because massive objects make things
It changes the property of the medium in such a way that whether it's increased density or a reduction in stiffness, it could be one or both or just one. I'm not certain. Okay. It changes.
Okay. So I guess that's the thing that I'm trying to understand is, so I'm surprised because you're saying that the speed of light is faster, closer, is
slower.
Is slower next to massive objects. And in order for it to be slower, stiffness has to go down or density has to go up.
Yes.
Okay. And density has to go. I mean, I guess that works, right? Because if you're next to a massive object, you would expect density to be fairly high.
Yeah, but then it's all about these subunits, though, right? How many of them there are and how they're connected to each other. Like all of these dynamics in materials result from the network nodal interactions of these subunits as they displace one another.
That's true, but I think that what Chantal is saying is she's like, you cannot know if stiffness is going down and density is going up, or if it's the
What-
opposite, because this is a thought experiment. It's like the speed of light is supposed to be
Find out.
constant
Well,
everywhere.
by studying material science, like when you go to material science, I'm sure people have studied this. It just takes time, right? So, if you were like a team with people, we would say, hey, you go ahead and you spend 3 days and research this. So that's the challenge. There's so many parts, and I guess I'm hoping more people will see that there's something to it and start researching those questions. That's exactly one of those questions. How can we find out for sure, right? Can we make an experiment? Is there something about material science that uses this already? But we haven't read papers yet, right? So
Well, we have actually quite literally been thinking nonstop about this. And so, Shilas, you're trying to make this point. Show your face right now.
I'm sorry, I just look like this. I'm thinking, this is my thinking face. I'm not, people accuse me of looking mean and stuff, but I'm seriously just trying to hold on for dear life.
But I think that you're trying to make this case about the nature of the matrix, and because your doctorate is basically in materials science and elasticity and stiffness.
Oh.
And so like
God, why do you have to out me like
I'm
that?
sorry.
Dude.
It's the only way of explaining why you have such a hard time wrapping your head around this, because you have spent a tremendous amount of time thinking about it. And so I'm like, okay, can you settle this question of, because it seems like what Chantal is trying to get at is that there is some abstract way that you can think about the nature of the ether and how it relates to the materials inside of it that are massive, that gives us insight into what we should expect the speed of light to be next to those massive bodies versus away from those massive bodies. And in turn, that will reveal something about the properties of the ether to us. And so the question, I think, but this is, oh my God, I think that the question is like, what makes things massive?
This concludes the first part of our discussion with Chantal Roth. Next time, we will pick up with specific phenomena as they relate to the elastic ether model, including electricity, magnetism, and light. See you there.